Good morning, my name is Oris Schur, and this week in physics, for physics lab number 2, we're doing a lab on momentum. We're using an app that can be found at this link, which is the Walter Fendit link. We're doing a lab on momentum, and we're using the elastic and inelastic collision simulator. For the first portion of the lab, we have to calculate the momentum of both carts, the red and the blue cart, before and after the collision. So for the first portion, we have to set the weight or the mass of the cart to 0.5 kilograms, and its velocity is 0.1 meters per second before the collision. For the blue cart, we're setting it to 1 kilogram, and the velocity is going to be 0 meters per second. To calculate its momentum, you do its mass times its velocity. So for the first portion, we know that it weighs 0.5 kilograms, and we multiply it by 0.1 meters per second, and we'll get 0.05 meters per kilogram a second. For the second blue cart, we know that 1 kilogram times 0 meters a second is going to be 0. And then we have to add up both momentums for the total momentum of both carts. And we see here that 0.05 plus 0 is going to be 0.05. I've already have it set up here, so we're going to start the experiment. We see the red cart coming in, and it's going to hit the blue cart. The blue cart starts moving to the right, and the red cart starts moving back to the left where it came from. So now we're able to calculate its momentum after the collision. So after the collision, the red cart is moving at negative 0.0333 meters a second, and it still has the exact same mass. Negative in this instance indicates the direction which it's moving, so we know it's moving negative relative to where it started. So it started moving to the right, and negative would indicate that it's now moving to the left. It doesn't actually have a negative velocity per se, depending on how you think about it. So we're going to do 0.0333 times the same weight, which is 0.5 kilograms, and that gives us 0.01665, which I rounded to negative 0.0167. The velocity of the blue cart after the impact is 0.0667, and it still weighs the same. It still weighs 1 kilogram. Anything times itself is itself. And now we're going to add that to the initial velocity. Actually, I'm going to do subtraction because using negatives on this calculator is somewhat confusing and annoying. So I'm just going to use positive values for this because using this calculator to represent it is annoying. So we get 0.05, which is our starting momentum. So we notice automatically that the momentum before the collision is equal to the momentum after the collision. And that is the whole purpose of this lab, is to show that momentum is conserved. Momentum before a collision is always equal to momentum after a collision. But that is to say that it isn't an isolated experiment, and that there's no air resistance, there's no friction, there's no heat being generated, there's no noise being generated, all of which would take pretty much convert energy, or that momentum, which is energy, to a different type of energy. That's why if you did this with cars, if a car was moving, here, let's get our calculator out. We did this for the homework assignment. 1,000 kilogram car moving at, let's say 20 meters a second, something crazy. So the momentum it generates is 20,000 meters times kilograms per second. If it hit another car that was stationary, the momentum would not necessarily equal the momentum after, because there are parts of the car flying off, there's heat being generated, there's air resistance, there's friction, all of which would make this experiment not possible in the real world, but the physics applies very much so, and the physics is very real and exact. For the second portion of the experiment, we're setting the mass of the red cart to 1 kilogram, and the velocity of it stays the same. So red cart 1 kilogram, the velocity is still 0.1 meters a second. Oh, I'm sorry. We're changing it to, okay, I'll just read it. Set the mass of the red cart to 1 kilogram and its initial velocity to 0.1, which is correct, okay. Set the mass of the blue cart to 1 kilogram and its initial velocity to 0. So we're just increasing the mass of the red cart for the second portion. And so let's start and see what happens. So that's really interesting. The red cart becomes stationary and the blue cart begins to move, and they both weigh the same, and we see that the momentum, or the velocity of the blue cart after the impact, is 0.1 meters a second. So that means all of that momentum was literally transferred. The red cart's momentum went to 0 because 1 kilogram that it weighs times 0 meters a second is 0. And the blue carts went from 0 to 1 kilogram times 0.1 meters a second, which is 0.1. So we see that the momentum was literally transferred from one cart to the other, but momentum is conserved. And we'll see that in the third experiment as well. So the last portion of the lab asks you, what conclusion do you draw from this data? And I just went into explaining that in the first experiment, the moving lighter cart hits the heavier stationary cart. Most of the momentum is transferred to the stationary cart to push it away. The lighter cart repels back at a much lower momentum, but momentum overall is conserved. The momentum before the impact is still equal to the momentum after. In the second experiment, a moving cart with equal mass to a stationary cart get in the collision. The momentum is entirely transferred from the moving cart to the stationary cart. The roles switch. The one that was moving initially is stationary, and the stationary one is moving at an equal momentum. Momentum is conserved. In the third example, carts of equal mass and opposite velocities, but a combined total momentum of 0 kilograms per meters a second collide. After they collide, they go back in the direction they came from. Momentum is conserved. So in conclusion, in an isolated system, one without friction, air resistance, or other outside variables, the total momentum of two objects before the collision always equals the total momentum of the two objects after the collision. And that is very true, and we saw this in our lab experiment, which is really neat to see. And that's all I have for this week.